Yeah, let's see. So now that k factorial is, we have replaced this 2k with k factorial by using this inductive hypothesis. That is okay. Just need a pointer. Where is that pointer? Yes. And now we are going to change this 2 with something. And I am giving you that clue that this n is greater than or equal to 4. If you put k or k plus 1 into it, then k plus 1 would be greater than or equal to 4. K plus 1 is 4 or greater. It means if you have the 2, 2 would be less than this k plus 1. So I am going to change this 2 would be less than this k plus 1. I am going to change this with 2 with k plus 1. And then there, okay, because this 2 is less than, then we are not changing this operator also. So that would be inequality. That is no issue. By using that condition, I am going to change this 2 with this k plus 1. That condition is giving me that idea. That 2 is always less with this k plus 1. So by using that condition, we are changing that thing. And now this is the definition of the, if you have, for example, this is k plus 1, the next number. This is k factorial. For example, if you have the 4 factorial, which is 24, and if it is multiplying with what? 5. 24 multiplied with 5, the next number. What you will get? 120, which is the factorial of 5. Which is the factorial of? For example, this k factorial is what? For example, if you have 4 factorial, the result of 4 factorial is 24. So just this k factorial, here you have the 24, suppose, and next number is k plus 1. 4 plus 1 is what? 5. So 24 multiplied by 5. After multiplication, what you will get? 120. That would be the result for the 5. And the factorial of 5 is 120. So that's why this k plus 1 and k factorial is what? It is equal to k plus 1 factorial basically, according to the definition. According to the definition of the factorial function. The previous factorial, the result of the factorial of the previous number, when multiplying with the next number, you have basically the k plus 1. You have basically the factorial of the next number. This is the definition. So that is that thing, k plus 1 factorial, which we want to show that 2k plus 1 less than k plus 1 factorial. So that is what we are reached here. We are reached here. So now this shows that pk plus 1 is also true when pk, when our assumption is true. And if it is the case, then finally what statement you can say? That the p of n, which is 2 raised power n less than n, which is that one, is true for all integers n with n is greater than or equal to 4. And now these are the examples in the book which I have left. So you have to 2, 4, 5, and 7, and then 7 to 15. These are consecutive examples in the book with the illustration and solution. So you have to read and understand them for your exam next, for midterm 2 or final or whatever. For midterm 2 or final or whatever, you have to understand these examples. I'm not giving you the exercises because you are not at that level. I will check the midterm 1, and if you are at that level, then I can change my decision. Okay. Now, this is not the part of your CO, but anyhow, I am just giving you that information. Because mathematical induction is not only the thing, there are some other kind of inductions. For example, you have the strong induction. There is a topic that is called strong induction. So the step is again the same, but there is some differences between the mathematical induction and the strong induction. And there is something next coming up, structural induction, like that. So that have the same step, but have the differences. So you only have to just see the definition of this strong induction. And we can use this strong induction again for some proposition P of n. If you want to show that that P of n is true for all positive integers, that is the same thing. P of n is the propositional function, as you are supposing already in your mathematical induction. And these are the two steps again. Basis step in strong induction is again the same thing. Again the same thing. Either P of 1, 0, 4, 5, whatever. The difference is here. Inductive step. In the inductive step of mathematical induction, you suppose P of k, and then you go to the P of k plus 1, and you prove the Pk plus 1 by taking the assumption of Pk. But here, you have to start with P. If P of 1 is true, and P of 2 is true, P of 3 is true, up to P of k. And there is a conjunction between them. And when all these propositions with their values are true, then this Pk plus 1 is true. Then this Pk plus 1 is true for all positive integers k. So this is the difference. And here in mathematical condition, this condition is giving you what? P of 1 only, and P of k and Pk plus 1. P of 1, there is no P of 2, 3, 4, 5, 6, 7, no. P of 1, and then you will go directly to P of k, random, arbitrary. You went to some arbitrary number, P of k, and assuming that P of k is true, using that P of k, you proved that Pk plus 1 is true. So that is mathematical induction. But here, in strong induction, you are going with, in a series, P of 1, P of 2, P of 3, up to P of k. And if that all these things are true, if that sequence is true, then you prove something P of k plus 1 is true. That is strong induction. You are not taking anything random. Okay. So recursive definition. Now the topic is changed. So this is basically 5.2. And it is only 3 or 4 pages, just theoretical stuff, no mathematical stuff, with some examples. But you don't have to do that, because I am not giving you examples from that. Otherwise, I can give. But it is again the same thing. It is not too much different from mathematical induction. You can see the difference here. But at least you have to know there is some strong induction also. There's not only mathematical induction. So that's why I have presented that definition of strong induction here. And now recursive definitions. And now I am moving to the second part of the CO, CO5. I want to finish this CO in this week. And every week I will finish one CO in 4 hours, every week, inshallah. But in 1 week, I will have the quiz and the midterm. So I have 4 weeks, which means I have 16 hours. And then on every week, I have to finish 1 CO. 3 COs are remaining, 5, 6, and 7. So I will try to take 3 of your weeks for the COs, for the lecture, and the rest 1 week for your midterm and the quiz. And in this way, I think we can cover up all these things. So that's why, inshallah, in the next lecture, I will finish it off. because there are only 20 slides. So now I'm moving to the second part of the CO, which is what? Which is recursion. How many students are here who already know the mathematical induction before this introduction here? Any student? This was the question I asked in the beginning of this lecture. Any student who have already the knowledge of mathematical induction from any other course? So this is your first time? And if this is your first time, I hope that, I don't know, but this is my just Arabic word is dalil maybe. It is my argument that I have delivered this concept in a good way. Even I didn't get this concept of mathematical induction in a good way from my own teacher. But this, because I know, I remembered my time. So, but I tried my best to give you that concept with clarity, with the steps, how you are taking that k+1, how you are taking that pk, and how you are like that. Anyhow, so now recursive definition. Before going on to the actual topic of recursive methods is your actual topic according to the CO, because it is recursive methods, which means recursive algorithms. But before that, we are going through with this introductory stuff. Recursive definition. There are some definitions which you can. So you can use this recursion to define something in a sequence. In mathematics, we have the sequences, we have the functions, we have the sets. So you can use this recursion for these three things. Sequences, if something is in a sequence, you can use the recursion and you don't have to write that sequence or no. And that recursive formula that you will build will give you that whole sequence. And similarly for functions, if there is some function, and normally function have the domain and the codomain. So if there is a one value, that value will map on that. That value will map with the codomain or whatever. Or just take it as an example that if there is a function in your programming language, that function normally takes some input, argument, evaluate it, and give you the output. Take some value, give you the value, like that. You can say that some function cannot take any value and cannot give you any value. Yes, it is true. But in mathematics, what is actually the definition of the function? So it will map some value to some value. So recursion can be used for sequences, for functions, or for sets. So now we are going with the first definition, recursively defined sequences. We are going with the sequences first. And then we will go with the functions. And then we will go with the sets with one example only. I'm not giving too many examples because this is quite easy things. Just to give you an idea that how you can define something recursively. Something will be given to you. And if I ask that, give a recursive definition for that thing, then how you have to think. So this is that thing which I'm just giving that concept. So if we have a sequence, then you can define that sequence recursively. And what is recursive? This is just a picture. This is the full picture. You can divide that same picture into a smaller picture, and that picture is also showing the same thing. You can divide it further into that picture, and that picture is also showing the same thing. And similarly here. So if you have a problem, and when you will divide your problem with a smaller size, this is the big problem. And when you divide your problem with the smaller size, with the smaller data, and that smaller size of your problem is doing the same thing again, which you are doing with the bigger problem. And if you are doing it again, you are dividing your sub problem again, and you are doing the same thing again. This is called recursion. This is the general definition. The normal definition is that if in your algorithm or in your program, when your program or algorithm is in its statement, it's calling it again and again, that is called recursion. You will see that definition there in the next slide. But the general definition of recursion is that if you have some problem and if you divide that problem with small size, and that small size of that sub problem is doing the same thing, and you are dividing your problem and doing the same thing again and again, so that is called recursion, to find your result. Anyhow, we can define a sequence. So up to now, maybe you will not understand the definition of recursion, but when I will reach at recursive algorithm, then you will understand. So we can define a sequence recursively. Here recursively means using recursion. You can define a sequence by specifying how terms of the sequence are found. So there is a sequence, and in that sequence you have different terms, maybe 1 plus 2 plus 3 plus 4 up to n. If this is a sequence, or you can remove the plus 1 comma 2 comma 3 comma 4 comma up to n, if this is some sequence. So you can find any term in that sequence, you can find that whole sequence or any term in that sequence if you have the recursive formula for that sequence. The only thing you needed is the first value of that sequence, and then you can use that formula, recursive formula, and then you can have any number, and then you can have the whole sequence by using that formula. So this is what mentioned here. By specifying how terms of the sequence are found, how you will find the terms of the sequence from previous terms. So that if you have a sequence, you can define that sequence. How? You can use the previous term, and using that recursive formula over that sequence, you can get that sequence. For example, here we have the sequence of powers of 2. What is the sequence of? This is given to you. This is the given to you. A of n, you can say it's a variable used to represent the terms of the sequence. So A of n is equal to 2 raised power n, and n is what? 0, 1, 2, and so on. So when you will put 2 raised power 0, you will have 1. When you will put 1 here, you will get the next term. Put these values of n here and you will have that sequence. You will have that complete sequence. 1, 2, 2 raised power 2, 2 raised power 3, 2 raised power 4, and so on. You have that complete sequence. So this an is simply a variable which you normally use to represent some sequence. An, and this is actually that formula. An is equal to 2 raised power n. So this is just theoretical sentences for that mathematical sequence. So what is that sequence? Sequence of powers of 2, and n is 0. So now, but this is not recursive, okay? This is not recursive. This is not recursive because we are not using some previous term to get the next term. Recursive is something in which you use some previous term to get the next term. This is what we have seen here in the definition. So now we are going to say that this sequence an raised power 2 raised power n, we can achieve, we can get this sequence. We only need that if we have the first term. Okay, first term is given to you now. A0 is equal to 1. A0, n is 0. Okay, this n is 0. A0 is 1. A0, now first term is given to you, and then you can build your recursive formula to get this whole sequence, And if that recursive formula is this one, an plus 1, here n plus 1 means the next term. And 2an, this an means the previous nth term. An means the nth term of this sequence A. Nth term of that sequence A, you will multiply that term with 2, and that would become the n plus 1th term of that sequence. Do you have this sequence in your mind? This is what? This is that sequence. This one. Okay, just keep. This is that sequence. 1 plus 2, but plus is not there, okay? There you don't have the plus, but it is, you can imagine comma here. The first term is 1, second is 2, then is 2 raised power 2, then is 2 raised power n. So this is the sequence here by using an is equal to 2 raised power n. Now the first term is given to you, and it is asked to design a recursive formula for that. So the first term A0 is given to you. A0 is equal to 1, which is the n is 0 here. So put here 2 raised power 0. What you have? Something has power 0 is 1. So that is 1 is given to you. And now this is the recursive formula. This means n plus 1, n plus 1th term of that sequence A. This means nth term of that sequence A. Then you have to multiply it with 2. So now what? N0 is what we have here. When n is 1, so it will become A1, or just put A0 here. Put A0 here. When n is 0, A0 multiplied with 2. What is A0? 1. 1 multiplied by 2, so that would become 2. That would become 2. And what is this one? 0 plus 1. So A1. So now we have A1 is equal to what? A1 is equal to what? 2. We have by using that formula. And this formula is giving me the next term by using the previous term. By using the previous term. This is what the terms of the sequences are found from the previous term. This is the definition. This is the definition of recursive. This is the recursive definition of the sequences. Anyhow, now we have the A0, we have the A1. Now for what? Put this 1 here. When you have 1, 1 plus 1, it will become A2. And here A1. A1 is 2. 2 plus 2, 4. So A2 is now what? A2 is what? 4. And in this way you can go on. You can find your whole sequence. So what are the things needed if you want to recursively define some sequence? The first starting value of that sequence and the recursive formula. But in the questions, first starting value may be given to you, but you have to design that recursive formula by yourself. Okay. For these sequences, you can also use mathematical induction to prove them. As we already did. For this sequence, we are using mathematical induction to prove them. So here the last point is saying that for these recursively defined sequences, you can also use mathematical induction if you want to prove them. If you want to prove them. Okay. And I will start here in the next lecture because 10 slides are covered and 10 I will cover in the next lecture. So I am stopping here.